understand why de Broglie's work was so important, we need to first see an inherent contradiction created by classical mechanics and electromagnetic theory. We know that an object moving in a circle is constantly accelerated towards the center of that circle according to classical mechanics. Also, according to classical electromagnetic theory, it is said that an accelerating charge will emit radiation in the form of electromagnetic waves. Thus, an electron orbiting a nucleus should emit electromagnetic waves, and as a result, its energy should decrease. And in turn, it should spiral inwards into the nucleus and collapse the atom. So, an atom like this is obviously not stable. Also, the frequency of an electromagnetic wave emitted by such an electron is equal to the frequency of revolution. So, this inward spiraling electron will have a constant change in its emitted frequency. And so, the light emitted will have different colors. Thus, it would create a continuous spectrum. Unfortunately, experimental observations did not agree with any of these ideas. We understand that not only are atoms stable, but also that their spectra are very discrete, which means that we have a few lines surrounded by dark spaces. So why was there this contradiction? Given here is an atomic model of the lithium atom, proposed by the physicist Niels Bohr. It was Niels Bohr who made the modifications required to Rutherford's model by combining classical and early quantum concepts for a better understanding of atomic structure. He formulated 3 postulates for atomic models. Let's dive deep into them. So what are Bohr's postulates? The first postulate states that an electron in an atom could revolve in certain stable orbits without emitting any radiant energy. So it would not lose any energy at some specific orbits inside an atom. Now, Bohr's second postulate defines the stable orbit. It tells us where are these special locations inside the atom where this will happen. This postulate states that an electron revolves around the nucleus only in those orbits for which the angular momentum of the electron is some integral multiple of the quantity h upon 2 pi, where h is Planck's constant. Now, Bohr's third postulate states that an electron might make a transition from one specified non-radiating orbit to another of lower energy. When it does so, a photon is emitted and it has an energy equal to the energy difference between the initial and final states. So, the angular momentum of an orbiting electron is quantized and it is emitting a particular frequency. So, the angular momentum is L, denoted by L, and that is equal to nh upon 2 pi, where h is Planck's constant, n is the specific quantum number, which is a whole number, and pi is the obvious constant. And the frequency of this emitted photon is given by nu, as in the equation, h nu is equal to ei minus ef, where ei minus ef are the initial and final energy states, respectively, of this photon. But this raises a question. Why should the angular momentum always be some integral multiple of the quantity h upon 2 pi and not any other value? Louis de Broglie had an explanation for this question. According to de Broglie's hypothesis, all material particles, including subatomic particles like photons and electrons, have a wave nature. After de Broglie, another scientist named Davison, along with another physicist named Germer, experimentally verified the wave nature of electrons. De Broglie proposed that electrons in a circular orbit must be seen as a particle wave. So you can imagine an electron not as a point particle orbiting the nucleus, but as a wave spread out in space. We know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which are at nodes at the ends and form a standing wave in the string. In the analogy to waves traveling on a string, particle waves too can lead to standing waves under resonant conditions. Standing waves are formed when the total distance covered by the wave down the string and back is one wavelength, or two wavelengths, or any integral number of wavelengths. The waves with other wavelengths will interfere with themselves and the amplitude for those frequencies becomes zero very quickly, or those wavelengths go to zero very quickly. So, for an electron moving in the nth circular orbit having a radius Rn, the distance covered by the electron is equal to the circumference of the circular orbit. That is given as 2 times pi times Rn. According to de Broglie's hypothesis, standing waves of n integral number are formed in the nth orbit. So we have 2 pi Rn is equal to n lambda, where lambda is the de Broglie wavelength of the electron moving in the nth orbit. From wave theory, we already know that wavelength is related to momentum by the given equation lambda is equal to h upon p, where p is the electron's momentum, and that is given by mvn. Thus, we get the equation h nu is equal to nh upon mvn, and rearranging the previous equation, we get mvn Rn is equal to nh upon 2 pi. Given is the quantum condition proposed by Bohr for the angular momentum of an electron. This equation is the basis of explaining the discrete orbits and energy levels in the hydrogen atom. Thus, de Broglie hypothesis provides an explanation for Bohr's second postulate of the quantization of the angular momentum of an orbiting electron. But Bohr's model is not perfect, and the following are the limitations of the Bohr model. So what are these limitations of the Bohr model? Well, number one, the Bohr model is applicable to hydrogenic atoms, which means that the atom consists of a nucleus with a positive charge plus Ze and a single electron where Z is the proton number. So, the Bohr model is not applicable to more complex atoms. Second, the model is unable to explain the relative intensities of the frequencies in the emission spectrum. It is seen that different frequencies have different brightness levels in the spectrum, which is not something that Bohr can explain using these postulates. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.